The first notes for Chapter 9. This is Section 9.1. We're talking about significance tests. And this first portion here aligns with the case study on page 537. It says, do you have a fever? So let's take a look at that. All right, so I've got the ebook pulled up here. The case study itself says, sometimes when you're sick, your forehead feels really warm. You might have a fever. How can you find out whether you do? By taking your temperature, of course. But what temperature should the thermometer show if you're healthy? Is this temperature the same for everyone? Several years ago, researchers conducted a study to determine whether the accepted value for normal body temperature, 98.6 degrees Fahrenheit, is accurate. They used an oral thermometer to measure the temperatures of a random sample of healthy men and women aged 18 to 40. As is often the case, the researchers did not provide their original data. Alan Shoemaker from Calvin College produced a data set with the same properties as the original temperature readings. His data set consists of one oral temperature reading for each of the 130 randomly chosen healthy 18 to 40-year-olds. A dot plot of Shoemaker's temperature data is shown below. We have added a vertical line at 98.6 degrees Fahrenheit for reference. And remember, 98.6 degrees Fahrenheit is the accepted value for normal body temperature. So if I can just scroll down here, it seems like we've got a lot of dots below that 98.6 degrees line. Okay, and here's some summary stats you need to know about the data. For this dot plot, the sample mean, X bar, was 98.25 degrees Fahrenheit. So you might be able to guess that. The balance point would be just a little bit above 98 here, 98.25. The sample standard deviation for this dot plot, the temperature readings, was 0.73 degrees Fahrenheit. And if you'll notice, it looks like a majority of the dots are below that accepted 98.6 degrees Fahrenheit temperature, right? And in fact, it says 62.3% of those temperatures, of these dots here, were actually less than 98.6 degrees Fahrenheit. Okay, so this data sort of goes against what we might expect to see for normal body temperatures, even with some sampling variability involved. In red here it says, based on the results of this study, can we conclude that normal body temperature in the population of healthy 18 to 40-year-olds is actually not 98.6 degrees Fahrenheit? So do we have enough evidence here to make that conclusion that, hey, it's actually not 98.6 degrees Fahrenheit? By the end of this chapter, you will have developed the necessary tools for answering this question. Hallelujah. So back to the notes here, and of course I have an illustration of some kid getting his temperature taken. It says, what are the two explanations for why the sample mean, X bar, was actually 98.25 degrees Fahrenheit instead of what the accepted value was supposed to be of 98.6 degrees Fahrenheit? So there's two ways out of this. We've talked about these in class a little bit before. Well, either science is wrong and it's below 98.6 degrees Fahrenheit, or it could have just been some sampling variability that we had a group that had a lot of people end up being below that number. So there's two possible explanations here. The first one is the true population mean temperature is actually less than 98.6 degrees Fahrenheit. So some people might say, why else would we get a sample mean this low from a group that was that big, right? You saw the dot plot. If the true population mean wasn't actually just less than 98.6 degrees Fahrenheit. I don't know what it is exactly, but it looks like we have evidence that it might be less. Okay, the other side of that statistical argument is that true population mean is indeed 98.6 degrees Fahrenheit. It's not less. So it's actually 98.6 degrees. And we got our sample mean that was low just by random chance. So in reality, hey, there's nothing wrong. It's really 98.6. You just saw some sampling variability. That's why your sample mean was so low. That was just by random chance. And notice I use the quotes so I don't have to rewrite this stuff up here, the true population mean temp. Okay, so on this same train of thought about the fever, What are the two explanations then for why p hat was 62.3% instead of 50%? And if I can just go back to the book here for a second, the 62.3%, that was the proportion of temperatures in our sample that were actually less than that 98.6 degrees Fahrenheit number. So if you notice, a majority, right, 62.3% of these dots were actually below this blue line. So why was there a majority of people, right? P hat 62.3% instead of just 50%. So why would we expect 50% to be the proportion of people that were below that 98.6 degrees Fahrenheit? Well, if 98.6 degrees Fahrenheit is the true population mean, then in a random sample, we'd expect it to be about half above that and half below that. So if 98.6% or 98.6 degrees Fahrenheit, if that's actually the true population mean, we'd expect there to be about 50% of the observations above and below, not just have a majority of people below that number in this case. So what are the two explanations? Well, they actually mirror these two explanations, and you'll notice I'll color-code it here too. And they have to do with, okay, so then what is the true population proportion, P? Is it supposed to be 0.5? Is it supposed to be bigger than 0.5? Why did we get a p hat that was so large in this case? The first one being that the true population proportion of people with temperatures below 98.6 degrees Fahrenheit, so they're pretty chilly, is just more than 50%. So maybe our data is strong enough that we could just say, look, this proves that the true proportion is more than 50%. So the true population proportion of people who are chilly, right, they have temps below 98.6 degrees Fahrenheit, could just be more than 50%. On the other hand, this true population proportion, you might say it's actually 50%, and you just saw that large p hat, right? P hat 62.3, you just got that by chance variation. And notice I use the quotes again so I don't have to rewrite all that stuff. So there's two outcomes. Either it's actually more than 50%, our data really proved that, or the other argument is, your data's not that strong. You probably just got a high p hat because it was just chance variation. All right, let's take a look at the CEO example here for a second. It says, a recent study on the relative age effect and career success, evidence from corporate CEOs. And this was in Economics Letters 117 in 2012, apparently. It suggests that people born in June and July are underrepresented in the population of corporate CEOs. This is consistent with the relative age effect due to school admissions grouping together children with age differences up to 1 year, with children born in June and July disadvantaged throughout life by being younger than their classmates born in other months. Basically, they define the cutoff, and children that are really young and close to that cutoff might be at a disadvantage. In their sample of 375 corporate CEOs, only 45, which would be 12% of those, were born in June and July. Is this convincing evidence that the true proportion, P, of all corporate CEOs born in June and July is smaller than 2 out of 12? Okay, so why is 2 out of 12 important here? Well, we're talking about 2 months out of the year, right? June and July. So if you think about 12% was the sample proportion, and we'd expect 2 out of 12 to be the population proportion if we're assuming that all months are fair, right? So if you randomly selected a month that a CEO would be born in, if it were fair, then June and July, that would just be 2 months out of a year, so 2 out of 12, which as a decimal is 0.167. So don't make that mistake. 2 out of 12 isn't 12%, by the way, right? 2 out of 12 would actually be 0.167. So the question is that sample proportion 12% low enough, right, to say that things aren't fair, right? If things were truly fair, we'd see something about 0.167. Our sample proportion was only 12%. So is that strong enough to say things aren't fair? All right, so a common question you'll see, let's give the two explanations for why we might have got a sample proportion that was below 2 out of 12, right? Our sample proportion was 45 out of 375. Okay, so some people might say that was just due to random chance, right? The low sample proportion, the 12%, was just random chance. It's not convincing enough to say that CEOs are at a disadvantage. So that side of the argument would say there's really no disadvantage to June or July CEOs. So there's always that side of the coin that blames that difference on just chance variation. The other side of the argument says, well, that's just too convincing, right? That low sample proportion was because the actual population proportion is below 2 out of 12. So the other side of that argument says, look, this really isn't fair, right? That sample proportion is so low, you can't expect me to believe that the true population proportion is 0.167. So that side of the coin suggests there is a disadvantage to CEOs in this case. So the question is, which side of the argument do we stand on as statisticians? Which one should we choose? Right? Because we keep seeing these same two explanations show up in each case. So it says, how can we decide which of the two explanations is more plausible? And our job as statisticians really is to determine how likely it is that we would get a sample proportion this low. Right? How likely we are to observe a sample proportion this low. Basically, how rare would this be, right, to get a p-hat equal to 0.12, like we got in the CEO example? How rare would this be by chance alone? And this is under the assumption that CEOs' birthdays are actually fair, right? So if CEOs' B-days were truly fair, how likely are we to observe a sample proportion this low? Maybe that's too extreme for us, right? So that's our job as statisticians. And so this situation calls for one of my all-time favorite emojis, the thinking face. How likely is it that we would get a sample proportion that low just by chance if CEOs' birthdays were truly fair? Because if we get done and we're like, listen, this is way too rare to happen, we might say that they're at a disadvantage. We might be in this camp. But if we get done and we're like, yeah, look, there's a pretty decent chance, we couldn't really rule out just random variation, we might agree with this group. Right? So that's our job. Determine how likely this scenario is. And as far as the do step, right, when we go to crunch the numbers, there's a couple different ways we could go about it. I mean, we could conduct a simulation, right? We could easily do that on our calculator and distribute birthdays, right? There's 12 months of the year. We also might be good enough to do a probability calculation, like normal CDF, if we have some conditions. So both of those would be ways to answer the question. And the question is this: what is the probability of obtaining a sample proportion of 0.12 or less, right? Because I have to say or less because it helps support our argument. What's the probability we get a sample proportion of 0.12 or less if indeed the true population proportion was supposed to be 2 out of 12 or 0.167 if you rather? So that is the question that the think face here is really pondering. So as statisticians, people might come to us with their data, like the CEOs here might come to us with our data and said, look, only 12% of the CEOs we surveyed were born in June and July. What do you think about that? Well, how rare is it to get a sample proportion of 0.12 if it's supposed to be 2 out of 12 that's fair, right? If it's supposed to be 0.167, that's fair. All right, so we talked about those questions having two possible outcomes. Now we're going to give them a little bit more of a formal definition. They're called hypotheses. And one of them is the null hypothesis, and one of them is the alternative hypothesis. So the null, that's capital H with a subscript of 0. That's not an O. I know what you're thinking. Don't get carried away. That's capital H with a subscript 0. The alternative is a capital H with a subscript of A. So that's the notation for each one of these hypotheses. H sub 0 and H sub A. So let's start with the null hypothesis here. H sub 0, and notice I have a colon here, that's our original claim. So it doesn't suggest anything new or fancy. This is also the one that says, hey, relax, there's no difference here, it probably just happened by chance variation. So that's the null hypothesis. It's a statement of equality, or it says no difference. So this claim is the one that says, look, there's not that big of a difference. It probably just happened because of chance variation. Nothing has changed. Well, you can probably guess which side of the coin the alternative hypothesis suggests then. Right? So the alternative hypothesis, that's the one that suggests there's something new or different going on. Like maybe the guy from Calvin College at the beginning of the notes is actually suggesting the healthy body temperature is less than 98.6 degrees. So this is an alternative claim. It suggests something new or different. And basically, we're trying to find supporting evidence against the status quo here, right? So we're going to go against the status quo here. If you don't know what status quo means, that means like the typical everyday accepted value. We're going against that with the alternative claim. And then what are some common mistakes that kids make when they're stating these hypotheses? The first one, don't forget you've got to mention both the null and the alternative, right? So don't just mention the alternative, don't just mention the null, you've got to mention both of those. Another one, probably the biggest mistake I see kids make sure you're using population parameters when you're talking about the null hypothesis or the alternative hypothesis. What are population parameters? Well, those are things like mu, the true population mean, or p, the true population proportion. Make sure you're using those and not sample statistics like x bar or p hat. I shouldn't see those. I shouldn't see sample statistics in your hypotheses. So we'd like to say something, we'd like to make an inference about the population. So let's make sure in our hypotheses we're referring to population parameters. And then the bottom part of this page here, it says for each scenario, define the parameter of interest and state appropriate hypotheses. All right, for the CEO example, what's the null hypothesis, H sub 0, and what's the alternative hypothesis, H sub A? Well, the null hypothesis is just going to make the safe bet. It's going to say, look, everything's fair. There's nothing weird going on here. So if everything's fair for the CEOs, that would mean that this true population proportion, P, is actually equal to 2 out of 12. And remember, 2 out of 12 was actually about 0.167. So the null hypothesis here, it basically says the sample proportion, I know it was low, right? It was actually 0.12, right? So a little bit lower than 0.167, but it must have just been by random chance. So the null just says everything's fair, everything's equal, it's actually 2 out of 12. I know you got a different sample proportion, but that must have just been by random chance. So then our alternative hypothesis, which is actually what the sample data was sort of suggesting, was the true proportion actually somewhere less than 2 out of 12. I don't know what it is exactly, but our sample proportion p hat, it's smaller than that 2 out of 12 value. So the alternative would be, maybe the true proportion of CEOs is actually less than 2 out of 12 for those birthdays. So in other words, the alternative That's sort of suggesting that the sample proportion, if it's 0.12, that's really too low for us to ignore, which means that the true population proportion of those June-July CEOs must be less than that 2 out of 12 number. Okay, one thing you'll notice we haven't done here yet is we never defined the parameter of interest. We never said what P was. Right? You may know it, but we can't just assume like, oh, it's implied. People will know what P is. So I'll just, as a little note here, P is this part. P is the true population proportion of June-July CEOs. So that'll be really important, and we'll lose points if we don't have that. We have the two hypotheses, right? And we also have to say where P is whatever it is, right? We have to give P in context here. Okay, one final thing I want you to notice here, whether it's the null or the alternative, the parameter is the same for both, and the value we're comparing is also the same, right? So the values are the same, the parameter is the same. The only thing that's different, the null will always have an equal sign here. The alternative would have a less than sign or a greater than sign, or maybe just a not equal to sign. We'll get to that. So let's go to the final part of the notes here. Part B says Mike is an avid golfer who would like to improve his play. A friend suggests getting new clubs and lets Mike try out his 7-iron. Based on years of experience, Mike has established that the mean distance that balls travel when hit with his old 7-iron is actually mu equals 175 yards, with a standard deviation of sigma equal to 15 yards. He is hoping that this new club will make his shots with a 7-iron more consistent, in other words, less variable. And so he goes to the driving range and hits 50 shots with the new 7-iron. So being more consistent is really important to golfers, right? If you think about a circle that they might land in, they'd like to make that circle smaller. So they want to be actually really persistent with their shot. So the old standard deviation is 15 yards. To improve upon that, right, we need to be more consistent. In other words, have a smaller standard deviation. So one note I want to make, why are we focusing on standard deviation in this case? Because Mike is interested in being more consistent, so that's why we're going to focus on the true standard deviation of his distances with the new 7-iron. If Mike were to somehow become all over the place with his shot and have a huge standard deviation, that club would definitely be no good to him. So let's get our hypotheses here. Let's start with the null. Remember, we're talking about standard deviation, so both of these I should see as sigma. The null hypothesis says there's really no difference between the new club and the old club, right? So this one would say sigma is still 15 yards. So the null really says, look, you're getting the same old results. There's no improvement, even if you got a new club. The alternative, though, apparently Mike's buddy is suggesting that this is going to make him a better golfer, which means his standard deviation would actually be lower, right? He'd be way more consistent in his shots. Maybe on average, he's only about 7 yards above or below, right? So the alternative would be the standard deviation is now less than 15 yards. So in other words, the alternative hypothesis says the new club beats the old one. All right, I need to make just a little bit of room here because one thing we haven't done is we haven't really said what sigma is. So we've got our hypotheses, but what is sigma? In this case, we could say where sigma is the true standard deviation of Mike's distance when he's playing with a 7-iron. So we do have to define what sigma is in context in this case. All right, in the bottom of the notes here, what's the difference between a one-sided and a two-sided alternative hypothesis? And how can you decide which to use? So what we've seen so far, they've been one-sided alternative hypotheses. So we've got the null, we've got the alternative. The null will always have the parameter equals some value. The alternative has the same parameter, but it's either less than or greater than that value. So whatever the sample data is suggesting will tell you we're either suggesting the parameter is less than the original claim, or we say it's greater than the original claim. That's a one-sided alternative hypothesis, right? So it's either less than or it's greater than. The two-sided is the same exact setup. So it has the null and an alternative. The only difference for a two-sided is the alternative hypothesis could have not equal to. So it doesn't pick less than or greater than. It's just saying there's a difference, right? It might be less than, it might be greater than. We don't know which one it is, but we're suggesting it's either one or the other. So that would be a two-sided alternative hypothesis. So one-sided sort of makes you pick. You have to pick either above or below. Two-sided isn't really picky at all. It just says, I just disagree with the alternative. Excuse me, I just disagree with the null. So I'm going to say my alternative suggestion is it's just, whatever the null is, it's just wrong. I don't know if it's above or below, but it's definitely not equal to the null. So how can you decide which one to use? For the most part, they'll be one-sided. You just have to look for keywords. So if you look at the wording of the question, you might see something that suggests a two-sided, the not equal to one. The two words I look out for, if you say something in regards to there's a change, something's changed, or there's something that's different, right? Those would suggest the not equal to case. We're just saying that we don't know whether we're above or below the null hypothesis. We just know it's different, right? So when should you use that one? Well, just look at the wording of the question. All right, so we've learned all about hypotheses in these notes. We've got the null hypothesis, we've got the alternative hypothesis, and that seems like it's plenty for now. So that is all for these notes. I'll see you in class.